So I've called it sort of systems thinking training, and it's kind of to familiarize everybody with a little bit of the background of systems thinking, what we mean when we say systems thinking, how it can be relevant to the hub. So I'm going to start by giving like a bit of a background, and then we'll work into kind of definitions and practice and application. So I thought I'd start with a bit of a background to systems thinking and kind of where it has come from. So the nature of systems thinking means it really doesn't have, I suppose, a sudden invention or revolutionary origin. It's kind of a skill that we've been using for quite a long time to solve problems. But a lot of people attribute 20th century biological theories to the formalization of general systems thinking and general systems theory. And this formalization was thought to be the result of post-World War II development. So at this time, engineering design and processes were becoming more complex, market environments more competitive, and also computer processing becoming much more advanced. And this kind of drove system engineering methodologies. And at this time, they were used to try and understand the interactions, interdependencies, and influences of individual design units, the process that's being created, and the dependencies of development. But at their core, they have these four foundations that kind of come from this biological background. So we have, going through them kind of from left to right, we have emergence, hierarchy, communication, and control. Emergence is something that's used to enable complexity to be described in terms of a hierarchy of levels. This can be in biology, this is often attributed to how internal organization of organisms creates an entity. So for example, cells. So the collection of our cells creates a human. And that's kind of, these involves like emergent properties and hierarchy. And in this sense, each hierarchical level is different to another, and its properties are also different and irrelevant. So the properties of a cell are very different to that of tissues and organs, and that's kind of the hierarchy, I suppose you can think of there. This then leads on to the other two, which are communication and control, which essentially are argued as needed in order to maintain this hierarchy through regulation and sharing of information. So those kind of four foundations really form the beginning of formalizing this thing called systems thinking. But naturally, these things became of interest to lots of other disciplines. Ones that are quite notable are philosophy, engineering, and economics. And these are attributed to be like also heavily contributing to the advancement of systems thinking. And this probably gives rise to things you might recognize in these pillars here, just some applications that have stemmed from this kind of input of other disciplines. So I hope that that's a bit of a historical background and has given you kind of a beginning of kind of systems thinking, systems theory. From that, you can kind of understand that the main purpose of systems thinking is to aid us in interpreting and understanding and also managing the complexities of reality. But this can be done in various ways, and I've kind of tried to categorize how different disciplines or different tools might use systems thinking and apply it to different areas. So I've categorized these into systems thinking for quality, for value, for knowledge, environment, relationships, adaptation, and complexity. So kind of briefly running through these, systems thinking that's associated with quality is interested in the quality of relationships between components that provide a solution or achieve a goal. Then value, so this is where the entirety of the system, including its subsystems, which is something that we'll come on to later, is characterized by the integration of factors that intervene in the process of creating value. Then we have knowledge, which is where systems thinking is used to create information. This often uses continuous learning and produces knowledge. And then we have environment. So this is where systems thinking can be used to explore boundaries. But it's worth mentioning that boundaries don't just have to be physical, for example, like buildings or countries. Boundaries can be process boundaries, such as manufacturing a product, or psychological boundaries, such as how we mentally construct systems. Then we have relationships, which is systems approaches that are used to understand and manage and organize the relationships and functions within a system. Adaptation, like essentially for a system to be viable and stable, it must also be able to respond to external influences. And in this case, systems approaches can be used to study the adaptability and viability of systems. And then we have complexity, which is the use of systems thinking to understand complexity. And it's worth noting that these aren't exclusive. So often in systems thinking approaches, you find that they are concerned with multiple applications, and like a lot of them also seem more favorable than others. So now there's like a bit of a background to systems thinking, and then also this kind of these areas that it can fall into. I think it's worth also trying to define what this term means in a more kind of succinct way, not just for reference, which can be useful for the definition, but also trying to understand the core components and the elements. So I thought we could start at the beginning. So at its simplest, we could define systems thinking as its component dictionary definitions. So essentially system and thinking. As you can see, this already gives rise to themes of networks and interconnections, complexity, judgment, reasoning. But I think this also demonstrates a point where systems thinking is also considered as a tool and a skill in itself. And when you consider it as a whole, it begins to deviate between discipline, institution, and background. This deviation, something that we'll cover later, but basically the perspective of our the information that we are exposed to changes how we define systems thinking, and that can be seen in the various definitions. So here on the left, I've got a bit of a word cloud that's been formed from 10 different definitions that come from academia, institutions, the big words being those that appear the most, and you can also see here that more things begin to emerge, such as complexity, behavior, patterns, and skills. So I think trying to take both of those kind of the component definitions and these varying definitions from academia, I've come up with this sort of definition, or I suppose it's more of a description, into trying to encompass systems thinking. And I hope this might be a useful reference. As I said, you can, these slides are available. And also if the word systems thinking is popping up, hopefully this is something you can mentally refer to. So a skill set used for solving problems and answering questions of dynamic behavior by understanding complexities, either physical or conceptual, as a summation of relationships and interactions between hierarchical components to make a whole. And then I've gone on to say that this can be used to provide observations on the impact of externalities and interactions between components, also demonstrating why and how new behavior is generated through changes in state, and it can help produce future patterns. I've just highlighted in blue there some things that have come up that I would probably say are characteristics of systems thinking. So things that I think are probably essential concepts into understanding systems thinking. But I think that probably we can delve into these characteristics a little bit more and really try and understand systems and systems thinking. So for these, the characteristics of systems thinking, I'm going to be referring a lot to this text here, and actually I have a slide at the end of this presentation for some reading that actually Rich recommends for systems thinking, and this is one of them. This is by Donella Meadows. It came out in 2008, and it's called Thinking Systems, and I just think it's a very good book for kind of encompassing what we mean by thinking systems and how we can apply it, and what more kind of like also the philosophy of what it means. So she uses a lot of examples to demonstrate basic principles in her book, and I have picked out 4 quotes that from her book that I think are really really kind of sum up not just systems thinking, but systems themselves, like what is a system. And I think these are 4 very important quotes. I've drawn out just for everyone to look at, but I'd particularly like to draw your attention to the first one. So a system must consist of 3 kinds of things: elements, interconnections, and a functional purpose. So I thought it was quite a good way of summing up what a system is, and also in that sense, what it isn't. So again, taking an example from Meadows, I just thought I could demonstrate what she means by this. So she actually uses the digestive system as an example. So she says that it has elements of teeth, enzymes, stomach, and intestines. These are interconnected through the physical flow of food with a function and purpose to break down food and provide nutrients. I thought that's quite a nice way of summarizing kind of what a system is. But also she does give an example that doesn't have to be a physical system. So here's a social system, which is a neighborhood with elements of streets and houses and amenities interconnected by the movement of people. And the function, I suppose, varies on how dystopian you're feeling, but a function of either to socialize, to make money, to exist. And I think it's also important to talk about what a system isn't as well. And Meadows gives this example of a block of flats. And she says that if a block of flats is filled with strangers who don't, and they have no relationships, it is essentially what she calls is like a pile of things. They're not really connected. It's not a system. You're just looking at a pile of things. But once those social relationships form, you could say it's a social system. But also from a different perspective, you could look at this and say it's an infrastructural system that it's got water supply systems, and it's got, you know, the whole block of flats. So I guess in that sense, it represents your outlook, and I think we're going to touch on that as well a little later. I think another quote that I particularly would like to draw your attention to is this one at the bottom. So saying that out of one system, a completely new, never before imagined system can arise. And I think this touches on 2 things. So first, kind of like systems creating themselves, but also a concept called nesting, which is essentially systems within systems. So subsystems is how they're often referred to. And if we could go back to the examples here, like the digestive system itself is a subsystem, I suppose, of all of our like a nervous system, our like musculoskeletal system working together, and that I suppose you could say is a subsystem in itself. I also think it's worth noting that just because it's a subsystem doesn't mean it gets any less credit. They still have huge impact in the overall system. For example, I think if something was wrong with your digestive system, that your whole body would probably know about it. So don't underestimate the subsystems. So this is another characteristic of systems thinking that I'd like to address. And I've said it's a characteristic of systems thinking, but I suppose it's actually more of a characteristic of the person doing the thinking. And I'd like to just talk about framing and positionality and our mental boundaries and mindsets in systems thinking. So systems thinking is also characterized and susceptible to limitations of our own mental boundaries. Essentially, we are creating these systems. And the first thing that it can be susceptible to is framing. And I think that this is not necessarily a negative, but it's something that is to be aware of, and it is a characteristic of us thinking in systems. Framing is basically how the choice of information, how information is presented, ultimately influences how that information is processed by the audience, which essentially means that our mental capacity to think or process problems as a system will always present a system that has been influenced by our own exposure to information. So essentially, the systems that we see and we propose have our disciplinary, cultural, intellectual boundaries and also biases. It's also worth noting that framing can also lead to misrepresentation of problems if we don't address it and we don't admit it and share it. This is often a problem in social systems because by misrepresenting problems and issues associated with people and communities, you can misframe them, and this causes injustice and exclusion. And I think it's just you need to be aware of your own mental boundaries and mindsets of systems thinking. I suppose more relevant to us, this links to positionality. This is more based on your social and political stance. In this case of the researcher, in the context of the study, affecting the research process at every phase. So in that sense, framing positionality, which are kind of they're really important to recognize as part of our systems thinking, the way we think in systems, and they contribute to our mental boundaries and can limit them if we're not aware. So now we have a bit of background to systems thinking, we've defined it, looked at kind of the characteristics, and I suppose in some sense the limitations. So now, how do we specifically apply these tools and these frameworks of systems thinking? How do we begin to think in systems, and how do we begin to create systems? So I think the first thing to note is that systems thinking is a spectrum. So a spectrum that runs from hard systems thinking to soft systems thinking, but nevertheless a spectrum. And I'd like to point out here that they're neither's right or wrong, they're just different. You don't have to sit at either end, as I said, like you can sit in the middle. And I think these bullet points here sum up quite well the kind of polar ends of the spectrum and how they differ. But I suppose building on these more hard applications, these are often more structured, more analytical. Problems normally more easy to find. They normally have a single and an optimal solution. This might lead into things such as modeling or quantitative tools. Whereas soft systems applications are normally used for more ill-defined or not easily quantifiable problems. They're often more conceptual. And again, neither's a right or wrong approach. They often suit different areas. And also researchers will be more comfortable in certain areas, and it's a family of systematic approaches. However, the spectrum also does mean that systems thinking often exists, as I'm sure a few of you will probably feel that you've probably even explored systems thinking by these definitions before. And it often means that systems thinking sometimes exists in academia without explicitly stating it's a systems thinking approach. And as part of some of my work, I've tried to use a thing called a systems test to identify in water resources these areas that use systems thinking but don't state it as an explicit approach. And there are many of them. As you can see, this is just for some areas of water. So a lot of you may be even practicing these without knowing, according to my testing criteria anyway. So with that in mind, different systems thinkers will naturally be asking different questions to build their systems models. Again, neither are right or wrong. They just have quite different outcomes, I suppose. So here are some questions that I think really kind of summarize the difference between like a soft systems thinker and a hard systems thinker, the difference between issues and problems, I suppose understanding and engineering. But this question in bold is what I probably think is the biggest difference. So how you use systems thinking to understand complexity, or how you use systems thinking to engineer complexity. And I think this is demonstrated quite well in this little graphic here. So here we have a hard systems thinker and how they perceive their complex world. And we have a soft systems thinker and how they are perceiving their complex world. And I've tried to think about how this could be, I suppose, more relatable in the field of water. So I think that a soft systems thinker in this sense might be more interested in governance and socio-hydrology, ethics and policy, whereas a hard systems thinker may be more associated with supply networks, treatment systems, and urban water infrastructure. But I think this slide also demonstrates quite well that both of these are very important to the other one. It's very hard to have good governance without understanding the more hard systems in the process, and vice versa. And I suppose this also demonstrates, I suppose, a little bit of framing, and in like this, especially when it comes to your discipline, about how you see different parts of the water security system. And I've tried to kind of neaten this up a bit in terms of why the different perspectives are so important, especially in our work in the hub. So going back to that biological digestive system example, we could have a systems thinker here who they're concerned with the digestive system. We have another one here, and they're not in the same disciplinary field, and they don't really concern themselves with thinker one, but they're interested in the respiratory system. So they see this part of the system. Again, number three, not really in the same field as one or two, and they are concerned with this part of the system. And number four, again, not concerned with what systems thinker 1, 2, or 3, and they see this part of the system. But very neatly, all four of them are required to make sense of this complex whole, I suppose. But that doesn't just happen. They are required to communicate, to challenge each other's perspectives, and to kind of talk about why they see the system in each way, but also make sense of it. And I suppose in that sense, I could also demonstrate this idea of nesting and subsystems, and how this in itself would be a system within a system. So here we have systems thinker 5, who actually is looking at this. So I hope that's kind of illustrated well the sort of ideas of framing, but also the ideas of nesting in that kind of little example. But bring it back to water. So now I think going on to the hub and systems thinking. So why we need to improve systems thinking and systems practice in the hub, and why it is important to our work. So as I said before, many of you are likely practicing some form of systems thinking in your research already, but it's still important to continue improving systems thinking to benefit research and practice. I suppose after all, the aim is to create a good performing water security system, and that involves multiple disciplines, multiple perspectives, and also lots of data, as I'm sure a lot of you are aware. This links back to framing, with all our perspectives being important towards working towards the hub goals. And in that sense, framing isn't a limitation, but an aspect to be conscious of. And we will have something unique to contribute to, and share our perspectives. But if we fail to recognise our own framing and also our colleagues' framing, we may tackle the wrong leverage points and invest in the wrong part of our water security systems. So some of you may recognise this image. This is from a session in Ethiopia. And I thought this was probably a good place to start our thinking about systems, and how we will build, how to build our systems and making it more relevant to the hub. So this was a session conducted in Ethiopia about what are the key, what components do we think are essential for water security. And this goes back to that pile of things at the moment. This is not a system, it's a pile of things. It's a good pile of things, but nonetheless it is a pile of things, and it's not a system. For this workshop, the question was asked, I believe the question was asked, what are the key things that we need to think about in the water security system? And I suppose this is a good starting point. So we start thinking about systems by asking questions, but what are the right questions, I suppose, is the next thing. So this is again from Meadows, and it is a long list of how she suggests living in a world of systems. There's 14 items on this list, so I'm not going to go through all of them, as I don't want you to fall asleep, but I am going to address, I think, 6 that I think are particularly applicable to the hub and probably relevant to, well, I hope relevant to everybody here. So these 6 are understand and observe, mental models, information and data, quantity and quality, system independence, and interdisciplinarity. So suppose we start at the beginning. So understanding and observing is kind of the first place, I suppose, we start when we think about building systems and the questions that are related to this. So Meadow refers to this as getting beat of the system. By what that she means watching it work. So I suppose studying its beat, knowing its history, asking those who are involved in the system about it, and especially if they've been in it a long time. This leads to an understanding of the current state of the system from a more dynamic perspective. And this would lead to questions such as asking about the history of the system, what's working well, what is wrong. Something I think that's really important here is this question here, which is, if we continue without change, what will happen? But here are some questions that I think are related to that first point. And again, these slides are available on Padlet if you'd like to refer to them. I also think for this step, it's really important that we describe the system in its actual behavior instead of the lack of our favorite solutions, which is easier said than done, I suppose. So secondly, we have mental models. I suppose this links a little bit back to framing, how we interpret the systems. This has inherent assumptions and framing, which must be exposed to everybody that we're working with. The best way to do this is often through diagrams, but it's important to note that these don't have to be mathematical or complex. They can be words, pictures, art, music, just anything that demonstrates how you form connections. It's important to collect others' models, but also to challenge them. This leads to questions such as, what is my model? What are others' models? And how can we test them? So thirdly, we have information and data, something that I'm sure a lot of you are very familiar with. It's important to know that information binds the system together. It's essential for communication, for connectivity, and also for development. But this also has the power to distort systems and also bias systems if the information is incorrect. You need to know your data, obviously, and what you have and what you have not, and as well as how biased this is. This could be associated with these sorts of questions. What complete information can I contribute? Kind of the golden question here, what data do I have and what data do I need? And then I think also very importantly, am I withholding any information that might distort the system? And in that sense, information is not just data, it's insight, it's experience, anything kind of that could distort the system or even, and if you withhold it, sorry. And then moving on to the fourth point, we have what's important over what is quantifiable. So it's kind of, I suppose, links to data. Many of us like data. I quite like data. We like to measure things, put numbers to events and phenomena. But that can sometimes lead us to believe that what we can measure is more important than what we can't measure, which is often not the case in systems. If quantity is what we concern ourselves with in the system, then the output will be quantity. And it's important to concern ourselves with what is important, not what is easily quantifiable. And we're all very good experiences of quality. Everybody will be able to tell if something's not of good quality. If you go to buy, I don't know, a t-shirt and you can feel the material and you know it's not good quality, or you eat something and it doesn't taste nice. Everybody's very sensitive to quality, and it's the same for systems. So for example, things in the system that are important to the systems we work with but are not easily measurable, things I suppose like justice, democracy, security, freedom, truth and trust, which I would argue are just as important as those things that are quantifiable. So I suppose this leads to these sorts of questions here, whereas the presence is absolute quality and what is important to the system. So penultimately, we have system independence. This is kind of concerned with how in the system some things encourage the system to run itself, whether these are actors such as people and objects, or just people, or forces, and these will be in various places of hierarchy, but many will be lower down. And I think this point is mainly just to not intervene and destroy the system's own self-maintenance. So thinking about things as what encourages the system to run by itself. Do we need to empower certain aspects to aid independence? And what is the value of what already exists? And then lastly, we have interdisciplinarity. This is just kind of talking about how systems thinking crosses over disciplines, it crosses borders and comfort zones, and kind of the importance of following the system and not your own discipline, where you should be committed to solving the problem rather than being academically correct, I suppose, in that sense. And that requires embracing of learning, but also kind of admitting ignorance, and embracing those kind of intersections between disciplines. So asking questions sort of about admitting ignorance and following the system, and where is the system going. So I think that's kind of the main questions I would argue are important in kind of beginning to prompt systems thinking and kind of developing our own systems. So say now we have a system, like say we know everything about systems thinking, and we have this lovely system here, as demonstrated. So we have this system. What do we do with it? How do we intervene? How do we change it? And all of these things. And these kind of points of intervention are often described as leverage points. And there is a long list of places you can find leverage points and how to intervene in a system. And these are kind of ordered on this slide in decreasing level of impact. So up here being the best place to intervene, and down here being the worst place to intervene. So I suppose just picking a few out of random to kind of demonstrate what I mean by intervening. So say we pick rules. So these define the scope and the boundary of a system. By changing the rules, you change the behavior entirely. This can be demonstrated quite well with games. So for example, football. I don't actually play football, but to the best of my knowledge, it's two teams, a square pitch. To score a goal, you kick a ball into a net, and you're not allowed to touch the ball with your hands unless you're in goal. If you were to change any aspects of these rules, then obviously the game changes drastically. If you had three teams or a circular pitch, or you are only allowed to touch the ball with your hands. So that's kind of, I suppose, a demonstration of rules. And then I suppose we could also demonstrate reinforcing feedback loops. So where some behaviors give momentum to the behavior, encourage it to grow. A good example of this is the rich getting richer. So obviously, if you have more money, you can invest more of it. You can take kind of, I suppose, taxes, and it impacts your overall wealth less. So it's much better in that sense. So that's a reinforced feedback, the rich getting richer. It's much better to address that reinforced feedback rather than try to balance it. So for example, it's better to introduce income tax or inheritance tax over, for example, anti-poverty programs for those who are less fortunate, as a balancing loop. And then lastly, I suppose buffers. So an example of this intervention is kind of by increasing the capacity of a buffer, you can stabilize systems. This is quite far down the list though, because it doesn't really change the system as such, and it just kind of, if buffers are too big, your system lags. I suppose an example of this would be shop stock. So you can buy in a certain amount of stock at a certain frequency of time in order to not run out of stock. But if you were to massively overstock, it would just cause a huge lag in your system of like restocking and purchasing and selling. And I think another good way we can talk about this kind of intervention and leverage, I suppose, is in a context that's a bit more relevant or relatable. So this is a systems loop diagram for flood control for a reservoir. So we have net precipitation contributing, which is what that plus means, to the inflow to the reservoir, to flood risk, to reservoir release, and then that reduces the stored water. So in a sense, we can talk about how to intervene in a system and why some things are more effective than others. So if we start at the bottom, so the least effective, over here we have numbers. And here, unfortunately, you can't really change the numbers. It's outside of any of our control to change the net precipitation. So you can see here how that's not a very good leverage point. Going up is we have buffers, the kind of shop stock example I gave. So this is slightly more effective than numbers, but the way we could do this is we could over-design the storage capacity of the reservoir. This does reduce the flooding risk, but it doesn't really change the system. If there's a large rainfall event, the flood risk still remains. So you can see how that's more effective than numbers, but still not really changing the system. Information flows, which is above buffers, so more effective. So that's sort of who and who does not have access to information here. So we could have a forecaster who knows the net precipitation. We could have an engineer who has designed the capacity of the reservoir. We could have a local council who's in charge of communicating with stakeholders about risk, and then we could also have the public who are concerned with the risk to their livelihoods, and they would quite like to know that. But you can already kind of see here how information flows are more effective than numbers and buffers. This is kind of most easily demonstrated by adding people to the information flow. So obviously, if we only had a forecaster, then we don't know the design of the reservoir, don't really know the flooding risk, etc. If we just had the engineer and the forecaster, the stakeholders would not be able to be communicated with, and the risk translated. And then if we have everyone in the loop, we can already see that this system is, I don't know, I suppose a bit healthier. So yeah, essentially what could be achieved if you change the information access in the system. Moving up from that, we have goals, which is the purpose of the function of the system. Currently, the sole purpose of the reservoir is for flood control, which is a balancing behavior. We can alter the purpose of the reservoir completely. So this is an urban water supply loop. Again, we still have the reservoir here and the net precipitation. We can alter even more if we combine them, and the system behavior will change completely. And the top leverage point that Meadows references is transcending paradigms. So essentially the mindset in which the system operates. So the mindset of this system, you could argue, is flood risk is reduced when through reservoir release. And if this doesn't happen, then stored water levels become too high and the houses flood. Oops, the houses flood. However, if the mindset is changed, the risk can be completely removed. So the risk can be completely removed if there is a systemic policy change in an ideal world where we don't build on the floodplain. That's kind of demonstrates Meadows' point of how transcending paradigms, I suppose, is the best leverage point, and you see results quite quickly.